Thank you very much. Thanks to everyone for being here early morning. So, yeah, yeah. So, I will try not to put you to sleep anyway, maybe. So these are nice theta functions that Oliver wrote yesterday, and this will appear in some of later lectures. I'm not sure if they will appear today, so I asked Oliver not to erase this, but I will end up erasing them before explaining them. So if you want, I will leave them for a few minutes if anyone wants to copy them. But okay, let me start from from where we left yesterday. So yesterday I introduced some basic facts about conformal field theory in 2 dimensions. So we say that the data we're interested in this 2-dimensional CFT is mostly the chiral algebra. Okay, so there is some chiral algebra A which contains the Virasoro algebra as some central charge C, but might be bigger than that. And then we have an anti-chiral algebra, A bar, and we are interested. So these are algebras that are generated, like A is generated by all holomorphic fields in our CFT. And the holomorphic fields corresponds to states, okay, which are annihilated by L0 bars, so they have a 0 conformal dimension on the right, and they have some conformal dimension H with respect to L0. And so we can write a mode expansion, and we always write it like this with this H appearing here. And starting, so there's an algebra of these modes, okay, that generates essentially the chiral algebra, and we are interested in saying, in decomposing the Hilbert space of states of our theory into representations of the chiral and anti-chiral algebra. Okay, so the Hilbert space decomposes into a sum over representation of the chiral algebra, tensor representation of the anti-chiral algebra with multiplicities. Okay, and this H is both in this for holomorphic fields is both the spin and the conformal dimension, okay? Because the spin is H minus H bar and conformal dimension is H plus H bar, but H bar is 0 in this case. So these are words, so example, easy example. Actually, easing example. So the easiest is the Eisen model, and in this case, the chiral algebra is not even extended. It's just Virasoro, a central charge 1/2, and the same is the anti-chiral algebra. So representations of this chiral algebra, well, we have 3 unitary representations. One has a ground state with the conformal weight 0, a second one with the conformal weight 1/2, and the third one with the conformal weight 1/16. Okay, so these are the ground states that are killed by all the positive modes. Okay, and then we build the representations R0, R1/2, and R1/16 by acting with the Virasoro, with the negative modes of Virasoro generators on the ground state in all possible, okay, in all possible ways. Okay. So here one has to be careful, especially in this case, because not all these guys are actually linearly independent. There are some linear relations here. Okay, so one has to, and the easiest is that L minus 1 on H equals 0 is 0, for example. Okay, but so there are some linear relations here, but essentially these generate the representations. And then the Hilbert space, I have to decompose it into tensor product of one representation of Virasoro and the other representation of Virasoro. And the way the Hilbert space decomposes is I take tensor product of 2 of the H equals 0, and then tensor product of the H equal 1/2, and then tensor product of the H equal 16. And these are, and this is the, this is our theory. So for each of these guys, so the ground, there is a ground state which have conformal weights 0, 0, for example, in this case. So this is the vacuum, okay? And it corresponds to some primary field. So in this case, this is the just the identity. And here there is a primary field of weight 1/2, which is usually denoted by this epsilon. And this is a primary field of conformal weight 116, which is usually denoted by sigma. Okay, so this theory should contain all states corresponding to the holomorphic fields, and also all states corresponding to the anti-holomorphic fields, while they all sit in the vacuum representation. So the holomorphic fields corresponds to taking any state in R0 tensor with the ground state here, okay? Because this has h bar equals 0. The anti-holomorphic states are ground state here, tensor any state on the other side. So this contains all the holomorphic and anti-holomorphic operators, and then contains also things that are neither holomorphic nor anti-holomorphic when you take two random states. So which operators are, so we have a lot of holomorphic operators in principle, so what are they? Okay, well, of course we have the stress tensor, okay, but then we have also all derivatives, all the stress tensor, and then we have products of derivatives of the stress tensor, okay, at the same point. So one has to be careful when you take products at the same point, you have to do some regularization to throw away some singularities. But essentially, all holomorphic fields here are just given by products of derivatives of the stress tensor. That's because the algebra is just a Virasoro algebra. So less easy example. Are current algebras. So suppose your theory has some holomorphic fields, J1 of Z up to JD of Z, and that they all have spin 1 or conformal weight 1. Okay? So we can make a mode expansion as usual. So we call Jn A, Z to the minus n minus 1 in this case. And then the algebra of this mode is very, very much constrained. The possible algebra, JBN. The only possibility essentially is the following. We have I times a constant, if A, B, C, Jm plus n, C. And then we have another constant, K, delta A, B, delta m plus n, 0. Okay. This is the only form that the algebra of these modes can take, essentially. Okay? And these FABC are some constants, and this K is another constant. So with the suitable normalization, so if you want a unitary theory, with suitable normalization of this K, of these currents, this K should be a natural number, which is called the level. Okay? So holomorphic fields of weight 1 are called currents. So that's why it's current algebra. Okay. And this FABC actually must be the structure constants of a normal finite dimensional Lie algebra. Okay. These are structure constant of a Lie algebra, like SUN, SON, E8, whatever, or some Lie algebra G, which of course has to have dimension D. Okay. This is just a finite dimensional Lie algebra. Okay. So the algebra that you obtain this way is essentially an affine Kac-Moody algebra. And it's usually denoted, well, I use like a G hat with level K. Okay? So if you notice, the zero modes, actually, for the zero modes, if you put the M here, that should be, if you put the M here, so this is not looking at the nodes, right? So if you put the M here as it should be, this goes away, okay? And this you have just a zero mode. So the algebra of zero modes closes, and it's just a copy of the finite dimensional Lie algebra G, okay? This also tells you another thing, that if a CFT has such a Kac-Moody algebra, okay, such a current algebra, then it has some continuous group of global symmetries. So I have a global symmetry G, okay. So G capital G is a Lie group of global symmetries corresponding to the Lie algebra, small g. Okay, Lie group. Commuting with L0 essentially. Okay, and how is generated this G? Well, you take the zero modes of your currents and you exponentiate them. Okay, this is the zero modes is a representation of the algebra. You exponentiate them with some parameters, whatever you want to call them, and these are the operators that generate the Lie group. Okay, and so this guy contains also a copy of the Virasoro algebra at some central charge C. So the Virasoro algebra, you get it. Let's do here. So Virasoro generators up to a constant are essentially given by sum over A of GA M minus N GA N. Okay, and sum over N. Okay, so this with a suitable normalization that depends on the level and on the Lie, and the kind of Lie algebra that is standard. This is a copy of the Virasoro algebra at some central charge C that again depends on level and the algebra. Okay, so you have a Virasoro algebra inside here. So let me give you the easiest example. Okay, so the easiest example is U1 to the D. Okay, so you have D currents JA of Z where the FABC are all zero essentially. So you have an abelian algebra underneath. So the level doesn't really matter for abelian algebras because the K, you can, when you don't have the first term, then you can rescale your current so that K is equal 1. Okay. So let me write the modes of this guy in a slightly different way. Okay, I write them as AN instead of JN for abelian algebras. Okay, so what are the representations of this guy? So you always start with some ground state, okay, which is annihilated. So it will be labeled by some vector, as I will say in a moment. So this ground state is annihilated by all positive modes, okay, for all positive N and for all A. Okay, and then you take it to be an eigenvector of the zero modes with some eigenvalues. Okay, so this we denote by the, so this lambda is the vector of eigenvalues, and you can take any vector of eigenvalues. So here you have infinitely many representations essentially for any vector. And then starting from this ground state, you build your representation by acting on lambda with your alpha n. So this, the reason why I used alpha n, because this reconnects to what Holly said yesterday. So this is actually what you get in string theory. Okay, when you have the scalar fields xa that give you the position of your string, okay, in some space-time, then Ollie said that the derivatives of xa is a current, and so this is these are all commuting. These have weight 1, 0, so it's a current, and you get d commuting currents if you have d of these scalars. So you have d holomorphic currents, but then if you have these guys, you have also the anti-holomorphic currents, which are the other derivatives. Okay. So when you have these scalar fields in string theory, you automatically have a chiral algebra that contains U1 to the D, and an anti-chiral algebra that contains U1 to the D, the same number. Okay. And then you can decompose your Hilbert space of states into representation. So you have to give me a vector for the chiral algebra and another vector for the anti-chiral algebra. Okay. And what are these vectors of the ground states? where these are the left and right moving space-time momentum. Okay. So if your theory is uncompatified, the representations that you include are all representation where P left is equal to P right, but then you take any possible P left or P right. Okay, this is uncompatified case. And in the compatified case, if you put on a torus, for example, then P left can be different from P right, and they can have, and they are discrete. So this corresponding I'm putting discrete momentum and discrete winding numbers around the torus. Okay, so in our case, in our CFT, I wanted to have discrete spectrum, so I wouldn't do the compatified case, but that's essentially related to what Ollie said yesterday. One more quick example, because that I might need later, is let's say SU2 level K, just last, to see what happens with the non-abelian. So if you have SU2 hat level K, then you have three currents, okay, that we can call J3 and J plus and J minus, for example, okay. So let's call L, okay, the ground state, if you want. So you want this to be annihilated by all positive modes. And then, so now you have the zero modes of these guys that do not commute, okay, because they form an SU2 algebra. So you can only require a ground state to be eigenvalue under one of them, for example, J3, okay. So what do the other zero modes do? Well, they essentially mix the ground states one with each other. So in this case, what happens is that you don't have a unique ground state, so a unique state with the lowest conformal dimension, but you have a whole representation of SU2, of the zero modes of SU2 of ground states. And starting from this representation of SU2 of ground states, then you act with the negative modes and you build the rest of the representation of the affine algebra. Okay. Now unitary representations here. So I can label the ground states by which representation of the SU2 finite dimensional algebra I have. So you can have, for example, a singlet of SU2 of ground states. This has conformal dimension 0, so the vacuum. This will need for the vacuum. But then you can have, well, I normalize with integers, sorry. So, but this is a doublet, essentially of SU2, with some conformal weight that depends on the level. And then you can go up to K. Okay, so they have the doublet, then a triplet, et cetera, et cetera, et cetera. And then you can go up to K if you want to have unitary representations. And these are, and you have only finitely many if you want to have unitary representations. Okay, so these are only finitely many reps. So let me stress, okay, so in this case, again, the conformal weight, I can write the Virasoro generators in terms of this mode, so I know what the conformal weight is, and it depends on this. It depends on this cell. I can be more explicit for U1 to the D, just to be, forgot to be explicit, but let me be explicit for U1 to the D. So for U1 to the D, the Virasoro generators you can write in this way, M minus N alpha N, so you sum over N and you sum over A. Okay, so this is true for M different from 0. Actually, you have to, so this you go in all Z. Okay. For M equals 0, you have to be careful because the guys don't commute. Okay, you have to be careful with ordering. So for 0, this is the thing. You have a sum, 1/2 sum over the 0 modes square. And then what you do, you sum with the alpha A, N, and you go from 1 to infinity. So you put a positive mode on the right, okay? And with this normalization, then the ground state lambda has conformal way lambda square over 2, as you can see from here. Okay. So this is essentially, this is similar to what Holly did yesterday with, I think, with the convention that alpha prime should be 2, I think. I mean, that's just a matter of how you choose your dimensions, essentially. Okay, good. So that's it for chiral algebras. And now we go to torus partition functions, which is where modularity arises. So we put our CFT on a torus now. Okay. So as Oliver taught us, conformal structure, so the conformal structure on a torus is parameterized by this modular parameter tau. So we can describe every torus as a quotient of C by this lattice. So a torus corresponds to something like this parallelogram with 0, 1, tau, tau plus 1, and with these sides identified. Okay? So what we want to compute is essentially the most stupid correlation function on the torus, that is a correlation function with no operator inserted. Okay? So the vacuum correlation function. So we call it Z, and this will depend, of course, on tau. Okay? So morally, you can get so if you want, you can write it formally or not formally as a path integral, okay, on the torus. So you do some kind of path integral over all the fields of your theory, e to the minus s, if you know the action at least. And then what you have to require is that essentially the fields in your theory are doubly periodic. Okay, so phi of z plus 1 is equal to phi of z equal to phi of z plus tau. So the dependence on tau comes from this periodicity condition that you put on your fields when you do the path integral. But what is more interesting is the operatorial description of this guy. So what do you do from the operatorial point of view? So you can think of this direction as being your space direction and this as being your Euclidean time direction. So here you have a circle, okay? So what you do is you start from some state on this at this time, this Euclidean time, and then you evolve in Euclidean time, okay? How much do you evolve? Well, you evolve up to time tau 2, which is the imaginary part of tau. And you don't only evolve in time, you also translate a little bit your state by an amount τ1, which is the real part of tau, okay? And then if you want to glue, so you have this finite cylinder where your state evolves, and then if you want to glue the two sides, what you do is to take a trace, okay? So this partition function will be given by the trace over the Hilbert space of states of your theory of the operator that gives you the time translation, the time and space translation. And this is given by e to the minus tau 2h, e to the I p tau 1, okay? Where this is generator of translations on the time translation cylinder, and this is generator of space translation on the cylinder, okay? And here we have a minus because we are in Euclidean. And if you remember, there was a relationship between this H and P and the Virasoro generators that I told you yesterday. So there's something like 2 pi over L0 plus L0 bar minus C plus C bar over 24. And this was 2 pi over L0 minus L0 bar minus C bar over 24, okay? And L was the length of the space circle. So in this case, the space circle has length 1. So this guy is equal to 1. So instead of H and P, you can insert these Virasoro generators in the trace. And what you get is the standard formula for the torus partition function. which essentially you saw in yesterday's talk by Oliver, which is the trace over H of Q to the L0 minus C over 24, Q bar to the L0 bar minus C bar over 24. So you can do the calculation that this is exactly what you get, where, as usual, Q is e to the 2 pi I tau. Okay? Now, this thing, so the theory is conformal. This thing should be invariant under conformal transformations. So this depends on tau, but we know that when tau is related to tau prime, say by a SL to Z transformation, then the two tori are conformally equivalent. Okay, there's a conformal transformation that is given by rescaling the variable Z by C tau plus D, the one that, okay, as Oliver said. Okay, so what this means is that our partition function should be invariant under SL to Z transformations. This follows by conformal symmetries. Now, if you write this Z tau more explicitly, okay, for example, if you decompose your Hilbert space of states into eigenspaces of L0, L0 bar, okay, these are the eigenspaces, then the partition function is just a Q series, so you sum over H and H bar of Q to the H minus C over 24, Q bar, H bar minus C bar over 24, and then you have the dimension of H of these eigenspaces. So this condition tells you that you cannot just put whatever Hilbert space you want in your conformal field theory. When you give me the data of your CFT, you have to pay attention that the corresponding partition function is modular invariant. Otherwise, you haven't defined a real CFT, a consistent CFT. So this is a very strong constraint on the spectrum of your CFT. Now, some remarks about this modularity. So first remark, let's see if I remember all remarks. First remark, you might want to allow some, so if C minus C bar is different from 0, so this is a kind of anomaly, essentially, and in this case, you might want to allow for some phase to appear here, okay? So there will be some phase, let's call it chi, which depends on A, B, C, D, which might appear here, and it only depends actually on on A, B, C, D, and on the difference of the central charges. It doesn't depend on any other details of the CFT, okay? So this is just to anomaly. So what this means is that Z is a particular kind of modular function, but is modular possibly with multipliers. So we haven't introduced this concept yet, but when you put modular invariance, okay, you can also allow for some specific phases to appear here that depends on your ABCD, and then you are in a different kind of modular functions, or you can also define modular forms in this way, and these are modular forms of modular function with a given multiplier. Okay, so you can allow for this. Other observation. So so invariance under tau goes to tau plus 1. Okay. If you look at this, so a part of the C and C bar factors that can get you a phase if C minus C bar is different from 0, then essentially this tells you that H minus H bar must be an integer. So this is the spin of your states. So all spins of the states must be integral, which means that the theory is bosonic. Okay? H and H bar taken, each of these can be any real number, just the difference has to be integral. For example, the Eisen model, we had 116, 116. Okay, so the difference is integral, but the guys are not. So now you might be a bit worried because you might want to have conformal field theories with fermions, actually. And this reminds me that I skipped one part, but okay. I will tell you in a moment. So what happens with the fermions is the following. When you have fermions, in your theory, you actually have different sectors of your Hilbert space, as Holly explained yesterday. So you have a Navier-Schwartz sector, and you have a Ramond sector. Okay. So for example, suppose your Virasoro algebra is extended to n equal 1 super Virasoro algebra. So this is the case that is interesting for superstrings, for example. Okay. So you suppose the chiral algebra A is n equals 1 super Virasoro. Okay. What this means is that on top of having the stress tensor, which is holomorphic, you also have another holomorphic field, which is a supercurrent, which has a conformal weight 3/2. So it has a mode expansion, which is something like that. Okay. And this, okay, the algebra of this guy is close, okay, with the Virasoro. Okay, I'm not going to write the algebra, but this is essentially a supersymmetry enhancement of the Virasoro algebra. Okay, so now the modes here can be integral or can be half integral. Okay, and that depends on which sector of your theory you are acting on. So, okay, now it's time to erase this thing. Okay. So in particular, you can have a Navier-Schwartz sector. So in a Navier-Schwartz sector, what happens is that, well, if you are on the cylinder, so if you're looking at the space of states on a circle in a cylinder, then Navier-Schwartz sector means that your fermions are anti-periodic as they go around the circle on the cylinder. When you map it, you do a conformal transformation from the cylinder to the space without zero. That means that the modes of the fermions are actually half integral. Okay, so half plus an integer. Okay, so this is the Navier-Schwartz sector, but then you have another sector which is R, and in this case, your fermions are periodic around the circle S1, and here the modes are integral. Okay, so this connection between periodicity on the cylinder and modes here, I'm not going to derive it, but it depends on how fermionic fields transform under the conformal transformation that maps the cylinder to this plane. Okay. So now, what happens on the torus partition function when you have fermions? Well, when you have fermions, you have to tell me what kind of periodicity conditions you put for fermions around the cycles on the torus. So what happens is that if you put, so the only way to have everything invariant is to put periodic conditions on the fermions under both the A and the B cycle on the toric. Okay, so if you put periodic under the, with respect to the A and the B cycle on the torus for all your fermions, then you expect the partition function to be modular invariant, SL to Z invariant. Okay, but what does it mean to have periodic boundary conditions? Well, what this means is that your partition function, well, on the space circle, that means that you are in the Ramond sector. Okay. Actually, I should say Ramond because I'm putting periodic boundary condition both for holomorphic and anti-holomorphic fermions. So you're only taking the trace in the Ramond sector of your Q bar, but then periodicity in the Euclidean time direction, maybe a bit surprisingly, means that you are inserting a fermion number operator inside your trace. Okay. You would maybe expect the other way around, that the periodicity in time is no fermion number inserted, but things with the fermions get a bit tricky, and actually there's the same thing with the fermionic particles going in a loop, essentially. It's not special to this case. Okay. So if you are computing this trace where you only look at the Ramon-Ramon part of your spectrum, you take a trace of this and you insert this, then you expect this guy to be a cell to Z invariant. You can, of course, look at traces over other sectors, and you can also decide not to put this -1 to the F, but that corresponds to putting some anti-periodicity conditions around one or the other cycle or both. Okay. And then you do not expect a cell to Z invariance, because the cell to Z transformation mixes the cycles, okay, so changes the periodicity conditions. So you expect the other partition functions to be invariant only under a subgroup of a cell to Z that keeps your periodicity conditions fixed. Okay. Otherwise, it mixes the different periodicity conditions. So this is what happens with the fermions. Okay, so. Yes, they do, exactly, yeah. I will maybe say something about that, exactly. So under a cell to Z transformation, they transform into one each other, essentially. So all the choices of RR and SNS, with or without this, they transform into one each other. So this is fixed under a cell to Z transformation. The other choices are mixed into one another, okay? Right. Okay, last, but maybe most important observation is that this partition function Z that I defined is in general non-holomorphic. There is no reason for it to be holomorphic, and indeed there is this Q bar here. So this is bad, okay? No one likes non-holomorphic modular forms, right? So, so what can you do? What can you do about it? So one thing you can do is to use the fact that I haven't used that you are actually focusing on the chiral and anti-chiral algebras, okay, of your theory. So I haven't yet used this fact. So if you remember that your Hilbert space of states decomposes as a sum over representation of the chiral and anti-chiral algebra with some multiplicities, then you can write your partition function using, okay, you can decompose your trace in the same way, so you have the multiplicities that appear here, and then you have some function here, which are essentially the product of a holomorphic and an anti-holomorphic function. So I call these functions the character over I of t times the character over j of t, and this is actually complex conjugate. So what is this character? This is just the trace of q to the L0 minus c over 24, okay? But just computed on the representation Ri of your chiral algebra. Okay. So your representation, so the chiral algebra contains the Virasoro, so it makes sense to compute this thing here on the representation. And then for each representation, you give me this character, and then the partition function decomposes in this way, okay? Now, these guys are holomorphic, okay? But in general, they're not quite modular, okay? However, you can get close enough to being modular. So they're also, let me just also say, they are actually holomorphic in the interior of the upper half plane. They can have poles at the cusps. This is fine. So in principle, they're what I would say weakly. They're weakly holomorphic. Okay. So what are the modular properties of these guys? Well, in general, they can be quite nasty for a generic chiral algebra. But if the chiral algebra A has finitely many representations, then things get much nicer. So you have only finitely many of these characters in this case, and then in this case, one can prove that each of these guys is a weakly holomorphic modular function, so modular form of weight 0, not for a cell to Z though, but for some subgroup, and in general, you can take a subgroup, a congruous subgroup gamma n for some level n. Okay. So each of them, for each representation, is a weakly holomorphic modular forms for gamma n. Okay. Yeah, you can read out. Yeah, you can read out what the level is from the conformal weights, and okay, I will tell you in a moment how you find it, because you can refine a bit this sentence, and yeah. So okay, I will say take more minutes, and then I do 5 minutes. So. Okay, so these theories where the chiral algebra has finitely many representations, so this means here you have finite sum, essentially. These are rational, these are called rational conformal field theories. So just as an example, Ising model, Virasoro algebra central charge 1/2 has 3 representations. Then we have a rational CFT. Virasoro algebra central charge higher than 1, infinitely many representations. So this is usually not rational. SU2 level K, you have only finitely many representations. That's rational. U1 to the D, you have any vectors in R to the D, infinitely many, then this is not rational. Okay? So you have a lot of rational CFTs. You also have a lot of very interesting non-rational CFTs. So actually, one can refine this statement, and that's the last thing before the break. So you can say a bit more about these characters if you start to consider slightly more general objects than just modular forms, which means you can look at vector-valued modular forms. Okay. So a vector-valued modular form of weight k. Okay. I will mostly take holomorphic or weakly holomorphic or meromorphic in the worst case. Okay. So not non-holomorphic. So what is it? It's a function from H to a vector space. Actually, to a finite dimensional vector space or something which is like C to the n. Okay. And the transformation, okay, is that, so under modular transformation, this gives f of tau. Then you have a factor C tau plus D to the k that you usually want to bring out if it has some modular weight. And then, so this is actually a vector in a vector space. This is a vector in a vector space. And what you do, you just act on this vector with some matrix, okay, n by n matrix that depends on your SL to Z element. So this rho is a homomorphism from SL to Z to the group of linear transformations of your V. So do you have some representation of SL to Z on this vector space? Just said, and this transforms in this representation. And since SL to Z is only generated by the S and T transformation, you just have to tell me what is rho on T and what is rho of S, and then I will know what kind of representation it is. So what happens is that if you have all these characters here, so if you have a rational CFT, so you have only finitely many characters, then you can take all characters and take them as the components of a vector, okay, which depends on tau. So this defines you a function from the upper half plane to the to Cn, depends on how many characters you have. And then what happens is that this thing is a vector valued modular function, so it has weight 0. Weight 0 for some representation rho that depends on the chiral algebra, and that's one of the main ingredients that come with the chiral algebra. So if you want to have a modular invariant partition function, you have to know how these things transform under cell to Z, and you know it. And then what you have to do is to choose the multiplicities in such a way that the whole thing combines to be completely invariant under a cell to Z. So this puts constraints on the multiplicities. So you can use this. So you can use vector-valued holomorphic modular forms, or weakly holomorphic. So this is weakly holomorphic. Weakly holom. So you can use the theory of vector value weakly holomorphic modular forms to build these partition functions. Okay, next hour, we are not yet done because we want to find the monsters, to explain the monsters motion. So next hour we explain the monsters motion, so 5 minutes. Next hour, whatever is left. 45 minutes, whatever is left, maybe less. Okay. Good. So a couple of things that I forgot to say, but there was a question that, okay, useful question that reminded me that. So I mentioned two properties. One that it is modular forms for gamma n, and one that they are vector valued modular forms. So here I should add they are vector valued modular forms for SL2Z, for the whole modular group, okay? So how are these two things related? Well, the point is that there is always a big subgroup of SL2Z where this rho sends this big subgroup to the identity matrix. So it's the kernel of this thing. So the kernel of rho always contains some gamma n, okay, for some level n, and that means that the whole gamma n is mapped to the identity matrix, and then that means that each single component of this vector is actually invariant under this subgroup. So it's each single guy is a modular form for gamma n. Okay, but this statement here is stronger. Okay, because this tells us also that if you do a cell to Z transformation, they just transform into one each other and not in something else, which has nothing to do with these guys. Okay, good. So now I do want a holomorphic partition function to explain monstrous motion. So I don't want this non-holomorphic stuff. So how can I get something holomorphic? It looks like I always have to put these guys here if I want to have something which is modular invariant. But there is one exception to this, and the exception is that if I have a chiral algebra that has only one representation, okay, then I have, which will be the vacuum representation necessarily, because this has to be there, then this vector value thing becomes one-dimensional. So this is just a one-dimensional matrix, so it's just a phase, so at worst it's a multiplier. Okay, and then I have a nice modular invariant partition function. So what happens is that if I have a chiral algebra that has only one representation, I can build a consistent conformal field theory which has only contains the holomorphic fields in the chiral algebra and nothing else. Okay, so this is a very degenerate kind of conformal field theory, but because it means that I don't even have the Virasoro algebra on the anti-holomorphic side. So that's a bit odds with what I told you before, but you can think of it as having anti-holomorphic Virasoro algebra where all generators, well, all operators are just zero, essentially. Okay. So you have just a fully, you have just a chiral algebra, and this is what you call a holomorphic conformal field theory. Okay. Holomorphic CFT, or mathematicians would call it a holomorphic vertex operator algebra, which is kind of the same of a chiral algebra. It's a vertex operator algebra, so a chiral algebra with just one representation, which is the vacuum representation. So how do I build such a beast? Okay. So we don't know all of them. We are very far from knowing all of them, but we know some tricks to build them, some of them. Okay. And I will tell you one trick, okay, which is useful. So the trick is the following. We start with the U1 to the D current algebra. So you have J1Z, JDZ. So this is definitely not a holomorphic VOA, okay? But we can start to add more holomorphic fields to this and try to build a larger chiral algebra that has which has only one representation, maybe, okay? So every field in this chiral algebra will be anyway a representation of this thing, of this U1 to the D. So U1 to the D will be a sub-algebra of your full chiral algebra. So we know that the representations are given by some vector lambda, okay? And so we can build also the Virasoro algebra just starting from these guys. So the Virasoro algebra we have already. And actually the central charge of the Virasoro algebra that we get is equal to D, okay? So this is similar to taking D-free bosons, except that we don't, if you take D-free scalars as in string theory, you always have the anti-holomorphic fields as well. And here we don't want the anti-holomorphic fields. So you can think in terms of free scalars as a string theory, but that's not completely the right thing. The best thing is to start just with the U1 currents, okay, holomorphic currents and nothing more. No. Yeah. It's, well, yeah, it's similar to the, writing an action for, which is for self-dual. So yeah, that's similar into the. But yeah, this is if you want an action. if you don't care about actions, yeah. Okay, so you have to tell me which representation you put in. So I want holomorphic fields. So this will have only the weights under this guy. So this lambda will be some vector in RD. So I have to choose the vectors in RD to give me new states in our theory. So remember that L0, so the conformal weight of any guy like this is lambda square over 2. Now, I don't want to tensor it with anything else on the anti-holomorphic side. So this guy better be an integer, okay? I have the constraint from modular invariance of the partition function that h minus h bar must be an integer. H bar I want it to be 0, so h must be an integer. I'm looking at bosonic things. Okay. So I want lambda square to be an even number. Now, each of these states will correspond to some holomorphic field. Let me denote with the curly V of lambda, Z, okay, with this conformal weight in our theory. And so this lambda is actually so this theory has a U1 to the D as global symmetry, of course, generated by the zero modes, and this lambda is the vector of charges, essentially, and that's this U1 to the D. And then you also want, so if you have two operators with lambda and mu, then when you start to take products, maybe regularized product, these guys, then you want, so this will correspond to a state which has charges, which is the sum the two charges. Very, okay. So the charges add up, okay, when you take products of these two guys. So this what this tells you is that when you choose the set of all lambdas that you want to include, this must be closed under sum. And then you, of course, you want a zero. You want the vacuum which corresponds to lambda equals 0. So what this tells you is that your lambda that you have to choose must be take values in some lattice, okay? You must have a lattice L in your d-dimensional space, okay? And this lattice must be such that every lambda here must square to an even number. So these are called even lattices, even lattice. And actually this condition here also tells you that if you take the scalar product of any two vectors, this must be integral. Okay. This because, I mean, if lambda square is integral, mu square is integral, and the sum square is integral, then lambda dot mu must be. So if this is even, if all things are even, then the scalar product must be integral. Okay. So you can also write the lattice. You can also choose a basis, a d-dimensional basis of your lattice. So let's say lambda 1, lambda d, and then you can describe the lattice as, okay, integral linear combinations of your basis vectors. And then you can define also, you can look at the matrix of scalar products in your basis, okay? And this must be an integral matrix, okay, with the even numbers on the diagonal, right? Now, your lattice, so there's once you have a lattice L, you have also something which is called the dual lattice. So the dual lattice is given by all vectors, let's call them, okay, mu. So these are vectors in Rd in general, okay, such that the scalar product with any vector in the lattice is integral. Okay. So this condition here tells you that if you have an even lattice L, then it is always contained in its dual lattice. Okay. So it might be smaller or it might be equal. And very special lattices are the ones that are self-dual. L is self-dual if L star is equal to L. Okay. And one can prove that this is true if and only if the determinant of this integral matrix of scalar products is equal to 1. So this is why self-dual lattices are also called unimodular lattices. That's the same thing. Okay? Okay, good. So now we have, so what we do is we take the chiral algebra, which is generated by the du1 currents and all these guys, okay, for all lambda in some lattice, in some even lattice. And now we hope that this chiral algebra has only one representation. And actually the way to see that it has only one representation is we build a character of the vacuum, okay, and we check if it is invariant under SL2Z. If it is invariant under SL2Z, that means that there are no other characters around, and then it is only one representation, essentially. So what is the character of this vacuum? Okay, so how do you build? So you have to take the trace of, so let me give a name to this chiral algebra. I will call it VL. Okay, V stands for vertex operator algebra, and L is the lattice, and these are called lattice VOA. So you can build a lattice VOA for, I mean, for any even lattice, and you get a bosonic VOA. But we are, and that's fine as a chiral algebra. But then we want the ones that are modular invariant. So what you do now, you try to build a partition function. You hope that it is a modular invariant, as a trace over this VL of Q to the L0 minus the central charge is D over 24. And what is this guy? Well, you can decompose this into representation of U1 to the D. So you get the sum over all lambda in the lattice, and then you get the character of each representation. So the ground state has conformal weight lambda square over 2. Then you have a minus D over 24. Okay, so this is just this just comes from the ground state, okay, with the charge lambda, and then you must act on the ground state with all your alpha negative modes operators to build the given representation U1 to the D. Unfortunately, Ollie did the calculation yesterday of what you get. What you get from all the oscillator is just a product from n going to 1 to infinity of u of 1 minus q to the n to the d, because you have the different kind of oscillators. That's exactly the same calculation that Oliver did yesterday. Okay. And then you can rearrange this thing, because here you have a q to the minus d over 24. Here you have this product, and the two things really mix very well, because they give you a Dedekind eta function to the power d in the denominator. And in the numerator, what is left is this sum of q to the lambda square over 2 for all lambda in the lattice. Okay. So this is the character of this partition function. So eta tau to the d is a kind of modular form. So we know that eta tau to the 24 is a cusp form, so that's an honest modular form. If this is not 24 or a multiple of 24, this is a modular form of weight d over 2, but with a multiplier. So it's not really an honest modular form because it has a multiplier, and that's why it doesn't fit into the classification of modular forms that should be only given by products, polynomials in the Eisenstein series. Okay, that's because it has a multiplier. Okay, so you want this guy to be a modular form of the same weight. So how does this guy transform? So let me write it somewhere else. So this kind of sum is what is called the lattice theta series. And these are nice ways to get modular forms. Lattice theta series. So this is, so I denote it as theta val of tau, which is this sum. Okay. And you can also write it as, you know, if you write your lattice in that way, you can also write as a sum of n1 and d in z of q to the ni qij and j over 2, I guess. So this is a sum over integers, and so it depends on this matrix q. Okay, here. So what are the modular properties of these guys? Well, under tau goes to tau plus 1, this is invariant, but this is built in from the fact that we took the lattice to be even, essentially. If the lattice is even, this color product, these are integer powers, and then you have this thing. Actually, you can define a theta series for lattices that are not even, and what happens is just that this is not invariant, but okay, that's what this is. So the nice thing is what happens when you do tau going to minus 1 over tau. And this, let me get it correct, although you probably remember it hard. So this you have to do some calculation here, but essentially using Poisson resummation formula. Okay, some useful formula, what you get is something like that in general. You have 1 over square root of the determinant of Q. This is the form where you can do the calculation best. You have 1 over square root of the determinant, and then you have minus psi tau to the d over 2. And then you have the theta series of tau, but not of L, but of the dual lattice. Okay? So this is the modular transformation of lattice theta series in general. And then what you can get from here is that this thing is invariant under, or is a modular form under this S transformation if and only if L and L star are the same lattice, or if and only if they are self-dual, because in this case, this guy goes to 1. And then you have this thing. Okay. Now, you might be worried about the minus I. Okay. So you have that theta L is modular form weight d over 2 if and only if the lattice is self-dual. So you might be worried about this thing here, but actually there's a theorem that tells you that even self-dual lattices exist only if D is a multiple of 8. Okay. So there are no even self-dual lattices with dimension which is not a multiple of 8. So this means that this guy actually is a multiple of 8, and then, so this is a multiple of 4, and the minus I just goes away. Okay? And we can also say, you can also write a bit how it looks like. And so what you get is something like, so you have, it starts from Q to the 0 because they have a lambda equals 0. So it starts from 1. And then you have Q to the 1. And then here you have the coefficient is the number of vectors with lambda square equal 2. Okay. And then you go on. The coefficient of Q squared is a number of vectors with lambda square equal 4, and so on and so forth. Okay, so this just counts how many vectors the lattice have at any given length. But the nice thing is that it starts with 1, so it's also actually holomorphic, okay, for Q that goes to 0. And this is nice because it's a modular form of weight D half, and then it exactly cancels the denominator. So what we get is that if the lattice is a self-dual, even self-dual lattice, then we got our chiral algebra with only one representation because the z tau is actually modular invariant. Possibly up to a multiplier, which comes from the eta downstairs. But that depends essentially on the central charge, which is the dimension D. I'm not sure. Yeah. That you can complete it essentially with holomorphic stuff. But that means that you can extend your chiral algebra. Because if they are holomorphic, that means they contain holomorphic fields, and that means that your chiral algebra is extended to something larger. Yeah. Okay, so examples. So you start with the smallest. Dimension is d equal 8. And here there is only one even self-dual lattice, which is the E8 root lattice. Okay? And so you get, so the theta function, this theta L for E8, so theta of E8 of tau is a modular form of weight for a cell to Z. Now, and this is an honest modular form, holomorphic and everything. There are not many of them. There is the Eisenstein series of weight 4. Okay, so this must be essentially the Eisenstein series of weight 4 up to normalization. So let me take a normalization different from what all is set. So I define, I like to call them EK of tau, which is again, it's the same Eisenstein series, but it's series scale, so it's the same as G, Eisenstein series, but this is scaled by twice Z of 2K. Now if I had the note, probably I would tell you right, but I think that's right. Yeah. Exactly. Okay. Let me also say that in the literature you find also that. So this is holomorphic. This is holomorphic, and that's different from. So if you look at this, the nice thing is that this starts from 1, and then you can also write the rest. So this is constant that depends on k, which I'm not writing down, and then you can write very explicitly the other things, because this is a divisor sum. This is sum 2k minus 1 of n over the sigma of 2k minus 1. Let me give it for 2k minus 1. It's just a sum over all divisors of n of d to the 2k minus 1. Okay, so you can compute it very explicitly. Okay, well, you need to know what this ck is, but you can. It's related to Bernoulli numbers and other stuff. I will not. So this starts from 1, so this is the right normalization for this guy. So this theta E8 is E4 of tau, okay? And this is 1 plus 240, this is the number here, Q plus whatever is that, Q square plus. And this is the number. So if you know the Eisenstein series, then you know how many vectors there are in this lattice of on any given length. So this is the theta series, and then the partition function is this thing. The partition function of the lattice VOA is this thing divided by eta to the 8 in this case, because we have a dimension 8. Your z of tau is theta 8 divided by eta tau to the 8. So this has a q to the minus 8 over 24, which comes from the eta function, but this is q minus c to 24, and this gives the multiplier, okay? And then you get the vacuum, and then you have 248q plus, etc., etc. So 248 comes from 240 from here, and there are 8 additional that comes from the theta series. So what are these guys? So this is the vacuum, okay? And these guys are the fields with the spin 1. So, okay, so what you discover is that you don't have only 8 currents, as you thought. Okay, you have the 8 currents, okay, spin 1, but then you have also other currents, V lambda, and this is a current whenever lambda square is equal to 2. Then this is weight 1, so this is also a current, okay? So actually your current algebra was not just U1 to the 8, but it gets enlarged by these guys. So these are called the roots of your lattice, the guys, and they are the roots of some Lie algebra, essentially. So in this case, that's a Lie algebra of E8, okay? And what this tells you is that if you put all these guys together, you get the current algebra, which is actually the E8 current algebra at level 1. Okay. Yes. Sorry.
Another thing, I think probably that G2K.
Oh yeah. Yes. Yeah, I used 2K. Yes, in my notes. That's true. You're right. Okay, and this happens more or less always. Essentially, you start with the lattice VOA with the U1 to the D, and this more or less is somehow is the Cartan subalgebra of what will be your true Lie algebra. And then you have to add all guys with the length 2, and that gives you usually a non-abelian current algebra. And in this case, this is all there is, actually. Your vertex operator algebra is this guy. And this comes from the fact that the lattice, you can take a basis of your lattice, which is just given by vectors of square length 2. Okay, this already generates the whole lattice. So you can go on with like this. So you can take d equals 16. Then you have two lattices. I'm super late. What time should I finish? At 11? Trying. So you have d equals 16. You have two unimodular lattices, which is E8 plus E8, essentially, so two copies of E8. And then you have a guy which is called D16 plus. Okay. So D16 plus is something which is, well, if you know what it is, so this is the root lattice of the SO32, the algebra. Okay. And then, but this is not enough, you're adding some other translate, okay, of the root lattice. So you're taking this root lattice. So this is generated just by the vectors of square length 2. Okay, but then this is not enough to generate the whole thing. You have to add some other vectors. And this S here, okay, if you know what I'm saying, good or not, but these S are the weight of a spinor representation of SO32. Okay, essentially. So you're taking a weight lattice will be with the root plus one spinor representation of SO30 from a Lie algebraic point of view. So these are even self-dual, and then these are modular forms of weight 8, and you don't have many choices. You have the square of V4. Okay. Also, it has to start with 1, so that's it. Okay. And this tells you that these two guys must be the same because we have no other modular forms of weight 8. Okay. So despite having the same theta function, these are very different lattices. Actually. And then if you take the partition function, okay, the partition functions of the two vertex operator algebras are the same. Okay, so this is theta of L of tau over eta tau to the 16. So they have the same thing, which is essentially eta 4 square of tau divided by eta tau to the 16. Okay, so this starts with the q to the minus 16 over 24, and then 1 plus 496 q plus. Okay, so same partition function, very different algebras, actually. Okay, the algebra of modes is very different. One is two copies of E8 level 1. Okay, and the other one is a SO32 level 1, which is, but then there are some other holomorphic fields that don't fit in the current algebra. So this is not the current algebra, okay, but it contains the current algebra of SO32 level 1, okay, plus some other holomorphic field, okay, that fits in essentially in a spinor representation of SO32. And you can go on like that. And the thing we're interested in is actually 24. And 24, you can play. Actually, you can prove that all holomorphic vertex operator algebras with central charge 8 or 16 are given by these guys. Okay, so there is one as central charge 8 and two as central charge 16. And these two guys, of course, actually this central charge 16, of course, are the guys that appear in heterotic strings. Okay, so in heterotic strings, you have a mismatch between the left and the right central charge, which is 16. You need a holomorphic CFT of central charge 16 to match the central charges. And these are the only two possibilities. And this gives you the E8 cross E8 and the spin 32 heterotic strings. Okay. Central charge 24, there are 24 even self-dual lattices. So you can usually, so these are called Niemeyer lattices. They were classified. And you can label them by looking at the sublattice which is generated by the vectors of square length 2. Vectors of square length 2 are very important in these lattices. So this is called the root sublattice. Okay. So sometimes the roots are enough to generate a whole lattice, as in E8. Sometimes you need to add something more. Okay. But you can label the guys by their square lattice. So this X is actually the root lattice. And then you have a list of 24 possible root lattices that give you even self-dual lattices. And they look at things like A1 to the 24, which means 24 copies of the SU2 root lattices, or A2 to the 12. So there are all guys with the SU2 root lattices, and then there are things like E8 cube, of course, this always works. Yeah, there are things like D16E8, of course, also this works, and then there are things a bit more mixed with the AED root, so SUN, SON root lattices put together, okay? And there is one which has no roots, actually, only one, and this is the Leech lattice, which is very special. This is the only even self-dual lattice of dimension 24, which has no roots. So all vectors, the shortest vector is, the shortest vectors have length 4. So they start from length 4 and then they square length 4 and then 6, 8, etc. Okay. And then what is the partition function of these guys? Well, here you have a little bit more room for the theta series, okay? Because you have E4 cube and E6 square that you can play with. But the theta series must always start with the 1, okay? And this fixes one coefficient, and then you can add something more which starts from Q, okay? Now, if you want to do something like that, what you do is you start, for example, from E4 cube, okay, which starts from 1, and then you have to add something which starts from Q, and there's a modular form of A12, and then you don't have many possibilities. You have delta, the cusp form, with some coefficient here. Okay, and the coefficient depends on the lattice. So here you have a little bit of freedom, okay, because this coefficient here depends on the lattice. So Oliver used the normalization for delta with some 2 pi things. So let me put eta tau to the 24 without anything, because it's easier, okay? And then, so what happens then for the partition function, though, is that you take this and you divide by eta to the 24. So it's not that you get much. You get E4 cube of tau divided by eta tau to the 24 with coefficient 1, because it has the vacuum. And then you have a constant. Yeah, you can't have much. And the nice thing is that, so this starts from Q to the -1. So this has no multiplier, actually. And this happens essentially whenever the difference between the central charges is a multiple of 24. You don't get a multiplier, okay? And it starts from Q to the -1, okay? And then you have 1 plus the number of currents in your theory times Q plus, and then you have all the rest. And here we are close to what we want. So this thing here is a weakly holomorphic modular function for cell to Z. It has a single pole at infinity. So this must be the J function plus a constant, okay? So this is actually equal to the J function plus another constant, okay? How do we call it? Some B. Okay, now let me not, so this is probably 744 actually. Okay, so this is actually this is really the partition function for the E8 cube. So the E8 cube is exactly this thing without anything else. So this is 744. So that might be wrong, but okay. So here, this I define with the 0 coefficient for the q to the 0 term. This is a 744, so this is just the thing. So this guy, so the number of currents is this C here plus 744 plus. Yeah. Okay. So we are very close to getting a holomorphic VOA with partition function is exactly j of tau. We want to have 0 here, okay? Because the j of tau that happens, appears in Monsters Moonshine was exactly the j function. So it was something like q to the minus 1. This we know that comes from the vacuum. Then we have 0, q to the 0, and this counts the number of currents in your CFT. And then you had the 196,884 q square, and this is common to all these guys, actually. They all have the 196,884 q square because the guys differ only by the constant term. Okay. Okay, this is a q because there's a q minus 1. Okay. And here we have a problem. We always, by the way I constructed things, we always has at least 24 currents because I started with 24 U1 currents. And if the lattice has some additional roots, then it can get bigger, but I cannot get rid of these 24 currents. So in all these constructions, this is never 0. Okay. And this is a bit of a problem because also the number of currents that you get never fits with the representations of the monster group. So these are not exactly the guys that I'm looking for. So I have to do something more complicated to get to the monster VOA, but this is the starting point. So the best that I can do to have less possible currents is to take the Leech lattice. Because the Leech lattice just have the 24 U1 currents that I put by hand, and then the lattice doesn't add anything because the Leech lattice doesn't have roots. Okay, that's the best I can do, and that's exactly the starting point. You can start from something else actually, but that's historically how the thing has been constructed. And yeah, I was hoping to to do it today, but I think it's a good time to stop. Yeah. Okay.